All right, in this lecture we're going to talk about stresses from thermal loads, and we're going to look at misfits. So we'll do thermal loading first. And as kind of the beginning to this, let's review what we already know about thermal strain and thermal deformation. So I have a bar. I'll just draw it as if it's sitting on a surface. And associated with that material is some coefficient of linear thermal expansion alpha. And it has some kind of cross-sectional area A. Its initial length is L naught. And I'm going to subject this to a temperature increase so that delta T is greater than 0. Now most materials expand when you heat them up. And I'm not going to worry right now about the expansion in the horizontal direction, but I'm primarily interested only in what's going on in the axial direction. We're still in a chapter where we're dealing with axial deformation. So it gets longer, and I'll exaggerate this change in length, but it gets to be a new length that's equal to the original length plus the change in length delta L. We know that the thermal strain, if this is the x direction of the bar, the thermal strain in the x direction is given by the coefficient of thermal expansion times the temperature change, alpha delta T. We also know that strain is the change in length divided by the initial length. So putting these ideas together, we can find that the change in length is equal to alpha delta T times the original length, L naught. Now, a little bit later on in the book, instead of using delta L, the book likes to use the symbol little e. And so the thermal deformation, they're going to call little e, is the same thing here, alpha delta T times the original length. All right, so we know that we have a strain in the material when the bar heats up. But the question I need to ask right now is how much stress is in the bar when it heats up. Well, the axial stress we know that we can find from a force divided by the cross-sectional area. And if this is free thermal deformation, the axial force is equal to 0. Here's my free body diagram with my internal force F, but there's no applied force, so that there is no axial stress. And I need to make sure that we understand that this is for free thermal expansion. We're going to learn how to constrain things later, but not right now. So this is for free thermal expansion. There's no stress, but we do have strain. Another thing that I want to point out is you may be tempted to use Hooke's law to relate stresses and strains. And it turns out that the Hooke's law that we have, sigma is equal to E epsilon, relate what are called mechanical stresses and strains. So even though we have non-zero strain, it's all thermal strain. And so by Hooke's law, we don't have any mechanical strain. So sigma is equal to 0. All right, so I'll make a little note of that there. Hooke's law relates mechanical strains only to stresses. All right, let's talk about a slightly different situation now. Let me get a new page. And let's take our bar Same one that we had on the previous page. And let's fix it in between two walls. So it's sitting there, but we put a wall on the bottom that it's resting on, and then we have something on the top that prevents it from expanding when it wants to. So here's our x direction again. We have our coefficient of thermal expansion, alpha, our cross-sectional area A. It's got some original length to it. And again, we're going to heat this up. Going to increase the temperature. Now, since it's fixed in between two walls, that means the change in length of that structure is equal to 0. Now, the strain in the axial direction is the change in length divided by the original length. That strain then would be equal to 0. In this case, however, the stress is not equal to 0. Because we have constrained thermal deformation. So this bar wants to get longer, but it can't. And if you think about it, as you increase the temperature, there's more and more of a resisting force pushing back into the material. We're going to end up having a compressive stress. Now, the way to think about all of this is that the deformation can be made up of two parts, a mechanical part and a thermal part. So we can say the change in length total is equal to the change in length mechanical plus the change in length thermal. Or with the symbols that the book's going to use now, little e total is equal to little e mechanical plus little e thermal. The mechanical deformation is given by our equation that we learned the other day, FL over AE, where capital E is the modulus of elasticity. And the thermal deformation is what we just talked about, alpha delta T L, where the L indicates the original length of the bar. So this is going to be the key into figuring out what's going on in these thermal deformation problems. Okay. Now, in this particular example that we're looking at right now, our total deformation is equal to 0. Okay, but we still have the rest of it we can write down, FL over AE plus alpha delta TL. Now, deformation, the mechanical deformation has a sign associated with it. It could be positive or negative. I'm going to assume that it has a positive deformation since I have a positive sign here. That corresponds to a free body diagram that would be in tension for this particular material. If I solve for my force F, the L's will cancel out, and F will be equal to alpha delta T times AE with a negative sign out in front, indicating that the force really is in compression. So this is kind of interesting. Now we have a formula that tells us how much the force is going to increase when we have a given temperature change for constrained deformation. Notice that it is got a modulus of elasticity term in it, and that's a pretty big number. We're talking about gigapascals, or we're talking about 10 million or so, tens of millions of psi. constrained thermal deformation can lead to very high forces very quickly, even with relatively small temperature changes. So it can be a pretty big deal if you have these temperature changes and you don't allow for thermal expansion. All right, let's talk about misfits next. And then we'll work a problem that has misfits and thermal deformation in it. Now, what I mean by a misfit is, suppose we have a couple of bars here attached in series to one another, and we have a force here. We could also increase the temperature in addition. But I'm exaggerating this gap distance. It's fixed over on the left, and it doesn't quite touch the wall over on the right side. There is some small value for the gap. And so this is a misfit. Maybe it's supposed to touch the wall. Maybe we need to find out what force it takes so that it will touch the wall. Well, in this case, we treat it in a way that's very similar to an indeterminate problem. Materials in series. We know that indeterminate problems have E total is equal to E1 plus E2 if it's in series, where this is section number 1 and this is section number 2. And if it was exactly touching the wall, then E total would be equal to 0. But if there's a gap, and if the gap closes, then E1 plus E2 is equal to the gap distance. So we need to put this in here if the gap closes. And at that point, you have a statically indeterminate problem. All right, let me set up a problem, and we'll take a look at an example. All right, so I got this set up. So let's take a look at this one. Here's a structure that's composed of 3 pieces that are hooked together. There's a couple loads on it, 5 kips and 10 kips. And we're also going to throw in some temperature change of the whole system of 250 degrees Fahrenheit. We're given some material properties. Coefficient of thermal expansion is 8 times 10 to the minus 6 per degree F, and the modulus of elasticity is 30 times 10 to the 3 KSI. The areas of section 1 are 1 square inch, 2 and 3 are both 3 square inches, and the length of section 1 is 12 inches, and sections 2 and 3 are 6 inches. What we want to do, and there's a gap between the end of the structure and the wall. I've exaggerated it so we can visualize it, but the gap is very small. It's 1 times 10 to the minus 2 inches. What we want to be able to do is find the forces in each of those 3 sections so that we can find the stresses, and in addition to that, find any strains and deformations and movements of those points. All right, so the way that we're going to approach this problem is first to see whether or not the gap closes. If the gap does not close, we have a statically determinate problem. If the gap does close, we have a statically indeterminate problem. Now in the textbook, in this section, I think all the gaps close because they're talking about indeterminate problems. But in a real structure that you may have to analyze on the job or something like that, it's a good idea to check and see whether or not these misfits end up closing or not. All right, so the way I'm going to write this down, let me write it over here, is the total deformation. It's going to be, for the entire structure, it's going to be the summation in this case from 1 to 3, but in general, depending on the number of pieces that you have, of the mechanical deformation plus the thermal deformation. FL over AE plus alpha delta TL. So let's write down here. Let me change colors. Write down first, we're going to see if the gap closes. So I'm just going to ignore the wall on the right. Now the total deformation, given the temperature changes, the lengths, and everything, we need to use statics to find the forces in each of the pieces. So I'm going to take, let's go this way. Let's go inside bar number 1 first. I'm going to draw a free body diagram and draw everything to the right. Oops, right there. 5 kips, and right here, 10 kips. So, force 1, I think we can see very easily, F1 is going to be 15 kips. Cutting inside section 2, drawing everything to the right of section 2. We're going to see that F2 is equal to 10 kips. And in section 3, if the gap does not close, there's no force over on the right side, so F3 would be equal to 0. So the total deformation is going to be equal to, let's see, F1, L1 over A1 and E. E is the same. Got everything now in pounds and inches. Plus alpha delta T L. Now the same thing for section 2. FL over AE plus alpha delta T L. Now F3 is equal to 0, so its mechanical deformation would be 0, plus alpha delta T L for section number 3. If we put all of these together, I end up getting 0.0547. Now 1 times 10 to the minus 2 is 0.01. So the gap does close. So this is now a statically indeterminate problem, and we need to use our materials and series approach to figure out what happens. Okay, let me pause here and put up a new free body diagram to explain what this looks like now that the gap is closed. All right, now switch colors here. So now that we know that this gap closes, what the free body diagram is going to look like for this structure is that we have an unknown force on the left and we have an unknown force on the right. Let's call this FA for point A, and over here point B, let's call this one FB. We've got our 2 applied forces of 5 kips and 10 kips at those locations. So the overall free body diagram for this says minus FA plus 5 plus 10 plus FB is equal to 0. We're going to have to go through and figure out what the forces are in each of these. Now, since the gap closes, we know that the total deformation can't be any higher than 0.01 inches. But that's still equal to the summation of FL over AE plus alpha delta TL. The alpha delta TLs are the same as what we found previously, but the forces are going to be different. So let's draw free body diagrams. I'm going to cut inside section number 1. And from this picture, F1 is equal to FA. Just assuming F1 goes to the right. That may or may not be correct. As a rule, I always like to assume that the forces cause positive stresses in the material, positive deformations. I'm going to cut inside section number 2. And in section number 2, we have the force on the left side, FA. We've got the 5 kips, and then we have an as yet undetermined F2. So from this picture, I think you can see F2 plus 5 minus FA is equal to 0. So F2 is going to be equal to FA minus 5. For my third free body diagram, I'm going to cut and look to the right. There's FB, and there's F3. It's easy to see that F3 is equal to FB. I'm going to switch back to blue, since that green's a little bit hard for me to see. Now, I go to my geometry of deformation equation, and I put in these unknown forces. Now, the forces are in terms of kips, so I'm going to write down F1, L1 over A1, E1 plus alpha delta T L1 plus F2 let me put this in pounds. That would be 5,000. L2 over A2 E2, which is 30 times 10 to the 6 psi, plus alpha delta T L, remember that segment's only 6 inches long, plus, for section number 3, FB 6 over 3 square inches, 30 times 10 to the 6, plus alpha delta T and L3. And then that's equal to 1 times 10 to the minus 2 inches, or 0.01 inches. Now, right now, this equation looks like we have 2 unknowns, FA and FB. However, from our overall free body diagram, we can say that FB is equal to FA minus 15,000 pounds. So this being equation 1 and this being equation 2, we can do a simple substitution and get that down to 1 equation and 1 unknown. At this point, what you would do then is you would solve for those forces FA and FB, which allows you to determine F1, F2, and F3. Once you know the forces F1 and F2 and F3, the stresses in each piece are going to be those respective forces divided by those respective areas. The deformation of each piece is going to be the FL over AE plus alpha delta TL for each piece. The displacement of these particular points, the displacement of this junction right here, will depend on the deformation of bar 1. The displacement of this point will be the deformation of 1 plus 2 plus 3, which is going to be 1 times 10 to the minus 2 inches. And so just like we work these other problems, we can figure out the deformations. All right, let's talk about one other thing, and we'll kind of summarize the important parts of today. But we want to talk about situations where you may have non-uniform heating. So sometimes what you'll see on engines are cooling fins and cooling rods. Sometimes very hot. It's a heat source. And in order to cool this off, sometimes they'll put rods or fins on the engine. Now we're going to look at this as if it were rods, but it's kind of typical sometimes to see fins. The point is, if you have a heat source over here, and over here is air, maybe even blow cooler air over it, you have a thermal gradient. Now, what the exact temperature distribution looks like can depend on the heat transfer characteristics. But for now, just to kind of keep things simple, let's just kind of assume we have what that picture, what that graph of temperature with distance looks like. Maybe it's linear. So on this axis is temperature, and on this axis is distance. Because the temperature is changing throughout, it's not uniform, the material next to the engine is going to stretch out more than the material away from that heat source. We're going to get a non-uniform thermal strain in this bar. That's going to cause non-uniform deformations. In this case, if we want to calculate the thermal deformation, the equation we want to use then is going to be an integral along the length of that bar of alpha, which could depend on position, the temperature, which in this case does depend on position, dx. So this is what you'd use if you have non-uniform heating. If we have a constant delta T, then and alpha, then this would integrate to be our usual equation for thermal deformation, not strain now, thermal deformation, alpha delta T times the length of the bar. Okay, let's save this file. And let's hit a couple highlights here. Most important thing today is our thermal deformation is made of 2 parts. Our thermal deformation is alpha delta TL. Our mechanical deformation is equal to FL over AE. And the total deformation is made of 2 parts. The mechanical plus the thermal. So this will be FL over AE plus alpha delta TL. Okay, so that's the important thing I want you to understand. And the other thing is statically indeterminate problems and misfit problems, they work similar to what we already have learned about, except you just throw in this extra thermal term. If you don't have thermal, then the delta T is equal to 0, and you just work with the mechanical part. But if you have any kind of temperature changes, the deformation of that due to that temperature change has to be accounted for. And it may or may not be overcome by the mechanical deformation part. All right, give those homework problems a try, and do contact me if you have any questions.